I'm Vijay Guruji, Director of R&D at IEEE Semiconductor. My talk is basic over system design. If you have attended my tutorial, it's very similar with some this thing. Right? So as you know, power electronics is ubiquitous, right? They're everywhere, right from your wristwatch to rockets and satellites and everything, right? So this also you can see the power rating of systems are being pushed, right? So we're consuming more and more power. How do we design systems to handle such powers, right? So in India we have very limited palette in terms of materials, right? When we have to design high power systems, we just keep paralleling things, right? Especially the advent of EV two-wheelers and three-wheelers. Unfortunately, battery voltage is very low, but you want high torque, high pickup speeds. So the HP ratings keep getting pushed. That means we are pushing 500 amperes close to that, right? So, but one single device can give you that kind of current. So we keep paralleling in various different ways, right? This is service mount. These are like metal core PCB. In India, we have only PCBs or metal core PCBs are available. Both are not very good in terms of thermal management, right? So there are other techniques which are beyond the cost realm of Indian designers, right? So doing this will increase your cost. Also, effectiveness of the utilization of the device also suffers. I'll walk you through that, right? So these are some of the things that you see in Europe, Japan, modules, right? You use ceramic substrates and all. These give you also better performance, right? So, like you can see, right? One thing with paralleling is the efficacy goes down after you parallel 3, 4, 5 devices, right? If you use a device, one device, you get 100% IS1. When you put 2, you get 50%, right? 3, you use 33%. So in the first parallel, you got 50% reduction, right? Then you got 17% improvement, right? As you put more, we can see the ISN doesn't keep going down, right? So you're putting beyond 4, you basically put 10, 15, 20, you get very little improvement in the ISN, right? So you can see the current as well, right? A 300 amp device you take and parallel 10 devices, per device basically you get 95 amperes, right? Per device. Correct? So that means your efficacy is now 1/3 when you parallel 10 devices. You're paying a lot of money, but you don't get much benefit from it, right? So this is how the modules are made, IPMs, the ceramic substrates, wire bonds. So because ceramic substrate is 100 times better in terms of thermal coefficient, right? But it still suffers from the trace fields. That means current density in the traces is going to be still very high, even they give you better thermal performance. So there are still trade-offs here, right? So sometimes you see companies putting copper bus bars, lead frames. So basically everything stacks up, right? In terms of processing, in terms of cost, in terms of complexity and reliability, right? So for us to optimally utilize the device performance, we need to understand the anatomy of the thermal cycle, right? So it's very important. If you being a good electrical engineer is not going to make you a good system engineer. You need to understand the thermomechanical impact of it, right? So if you look at the thermal stack, the chip is sitting here, then you have the solder, you have the copper. So basically this is your TO220 or T2pack, TOL, that is just composition. Then you will solder that onto a PCB or a metal core substrate. Then you put a thermal interface material and slap it onto the heatsink, right? So each layer will add certain resistance, right? For example, you put a Kapton tape here. The resistance of that is going to be quite large. This is the thermal resistance. So majority of your temperature drops in the thermal interface material. That's not going to give you any benefit, right? Ideally, you want to drop as much temperature as possible across the chip itself. That will give you the maximum amount of current. So I see, go to customers and see, right? Put some Kapton tape or some very cheap tip material. They're paying a big price for it, right? So if you want to be a good system designer, you need to understand how the thermals work, right? Also, I do a lot of systems. 70% of my effort, cost is in the thermal management system. Either heat sinks or plastics around it. The actual device cost is not the maximum cost in the system. So I encourage you to pay attention to that, right? I'll give you one example. This is a MOSFET data sheet from Infineon, right? What they show is internal thermal resistance is 0.4 C per watt, right? So what it says is if you make a minimal footprint, like normally that's how we do, right, in the PCB, as much as the device pad, we put out so much copper. If you do that, you get 62 K per watt, right? But normal ZX standard tells you, you put 1 inch square copper pad, that's how the thermal resistance is defined. You will get 40 C per watt, right? So if you translate that into the current based on this formula, so if the device itself is capable of 342 amperes. So Infineon's rating is 350. There's some rounding errors and all this stuff, right? But if you use your minimum footprint, you're going to get the 27 amperes on the PCB. So less than 10th of what you're paying for, right? But if you are generous, give you 1 inch square pad, which no PCB designer will do, right? So you will get 34 amperes, exactly 1/10, right? So the stack I have from Gamtrek, I can get 0.65 C per watt, right? So from 0.4 you get 0.65, I can extract 270 amperes from it. How I do it? That's a secret, right? But what I mean to say is there's a huge amount of improvement you can do by studying the thermal circuit, right? So this is at 25 degrees. Now nobody operates the device at 25 degrees, right? So this is 100 degrees, this is the case temperature. Now things get even dicey, right? The device is now capable of 240 amperes. Here it says 250, right? Now your minimum footprint will give you 19 amperes, and the generous 1 inch square gives you 24 amperes. If your system needs 240 amps, ideally you'll go on parallel 10 devices, right? But we also saw paralleling 10 devices doesn't give you 10x current, right? So my point here is look beyond RDS1, look into the thermal management system, right? So I can pull 190 amperes out of that device, right? So there's a world of difference you can make. If my system needs 240, I can just do with two MOSFETs, which regular PCB design needs 10 plus, right? So this is the module, right? So Like here, like any battery pack you open, there's a charge discharge switch, whole bunch of MOSFETs is in, right? Here you have 10 plus 10 MOSFETs. These are charge discharge. The entire cost of BMS is determined by this, but the you will spend maximum amount of time developing these and optimizing your BMS algorithms and all. But your cost comes from here, right? So if it is more than 100 amps battery current, they use the contactors. Contactors, DC contactors, as you know, they're very short-lived, right? Because of welding and all the stuff. So we have that solid-state relay uses 4 plus 4 MOSFETs, right? Also, other thing to consider is the thermal transient-thermal impedance, right? So system often work in steady state continuously. There are, for example, you take an EV two-wheeler, right? You all drive in Bangalore. You will never drive at cruise speed, right? Start, stop, start, stop, start, stop, 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 right? That's a transient condition. The device experiences the maximum current during start stops, right? So that's where transient thermal impedance comes into picture, right? So this is in the data sheet, but how do you interpret it is very important, right? So that's how your junction is getting, basically when you start, a huge rush of current goes to the device, your junction temperature will rise like that, right? This is the most dangerous thing for an electronic system. You can run your device at 150 degrees for hours together. That is not the worst condition. Because it's in a steady state, everything is settled, right? When you have a profile like that, you look at your stack, now from the mechanical point of view, each material, as we know, we studied in physics, has a temperature coefficient of expansion, right? So they expand and contract at different rates. Silicon is 2.5, solder is 25, so 10x more than the silicon. When you have a ripple like that, your solder is expanding 10x compared to your chip, right? So if this continues to happen, solder will basically crack. I've seen devices come back to the lab for failure analysis. Once the solder cracks, your thermal resistance increases. That exacerbates the situation, right? Your ripple will start increasing. So it's a downward spiral. So you will eventually have a catastrophic failure.